So we're going to do this example, which is another example of calculations involving equilibrium and Kc. It's also going to involve Le Chatelier's principle. So this is the question. They gave you the balance equation. They gave you the Kc value here, which is 1.2 times 10 to the 3. And then the question is asking how much of each substance in moles will there be at equilibrium in a reaction mixture that initially has 0.0100 moles of carbon monoxide, has the same number of moles of chlorine, and 0.100 moles of phosgene, COCl2. Okay, so I'm just going to go from this screen here to my sketchpad right here. And as you can see, I've started working out the problem already. So I'm just going to go through the steps so that you understand how we get to this point right here. So first thing I did was that I calculated the concentration of carbon monoxide, which will be the same as the concentration of chlorine. So these two are going to be the same because the numbers involved would be the same. The moles is the same for both substances and the volume would be the same. So therefore, both of them will have the same concentration of 1.00 times 10 to the minus 3. In the case of COCl2, similar process. The only difference is that the moles will be different. 0.100 moles in this case. The volume is still 10.0 liters. So we end up with this answer here. Now at this juncture, we have to ask ourselves, we know now that these would be the initial concentration. So that's why I have them here for the different substances. The question is, which direction the reaction will shift in order to achieve equilibrium, all right? Because these are not equilibrium values. So in order for us to do that, we have to calculate QC and compare it to KC. Now QC would be concentration of COCl2 divided by concentration of CO times the concentration of Cl2, right? So all we have to do is plug these values into this equation right here. And that's what I did over here, right? And I end up with 1.0 times 10 to the 4. So basically QC is equal to this. And when we compare to Kc, we see that Kc is 1.2 times 10 to the 3. In other words, QC is greater than Kc. So what does that mean? That means that the reaction will shift, if QC is greater than Kc, to the left in order to achieve equilibrium, all right? So basically what we have to do now is set up a nice table. So what I have to do, since I obviously have limited space here, I'm going to erase all this here. And then set up my ice table so that we can proceed to the next stage of the calculation. Okay, so first thing I'm going to do after I finish cleaning this is to write down the equation choose this first. Okay, so CO plus Cl2 to give COCl2, all right? Now the initial concentrations that we had from before, for the carbon monoxide, it was 1.00 times 10 to the minus 3, 1.00 times 10 to the minus 3, and here we're going to have 1.00 times 10 to the minus 2, all right? Now we said that the equilibrium is going to shift to the left. So therefore, what that means is that since the reaction, the equilibrium position will shift to the left, or the reaction will shift to the left, that means that as far as the changes are concerned, the change for COCl2, I'm going to call that minus X because we don't know what that is. So if minus X is a change for COCl2, then plus X would be the change for chlorine, and plus X would be the change for carbon monoxide, which means that at equilibrium, you're going to have, for carbon monoxide and COCl2, 1.00 times 10 to the minus 3 plus X, 1.00 times 10 to the minus 3 plus X, and over here you're going to have 1.00 times 10 to the minus 2 minus X, all right? So therefore, Kc will now become equal to the concentration of COCl2, which is 1.00 times 10 to the minus 3 divided by 1.00 times 10 to the minus 3 squared. And that would be equal to, oh, I'm sorry, this should be plus x here. And let me just erase this here. And down here, you should have minus x squared, all right? And that would be equal to the Kc value, which is given above, which is 1.2 times 10 to the minus 3. Now from here, it's a lot of algebra, which I won't go through. I would expect you to know how to do that. Let me just say that after solving, going through several steps, you're going to get a quadratic equation, which looks like this. 1.2 times 10 to the 3 x squared plus, or I should say minus, let me erase this here. So down here, you're going to have minus 3.4x, and then minus 8.8 times 10 to the minus 3 minus 3 equals 0. Okay, so what that means is that x, when you use a quadratic formula solution, x will turn out to be equal to 0.0016, all right? So, you know, basically you'll be doing your algebraic manipulations to get from here to here, and then you're going to use a quadratic formula to solve for x, and you'll find that x is equal to 0.0016. Okay, but we're not finished yet, because what the question is asking for is not x. The question is asking for the moles of each substance. So again, I'm going to need some more space. I'm going to do some erasure here, because what we have to do is to find out the concentrations first for each of the components involved, starting off with the carbon monoxide. And again, the concentration or the calculation for the concentration of CO would be the same as the concentration of Cl2, which would be equal to, according to the ice table setup, that's going to be equal to 1.00 times 10 to the minus 3 plus x, which is 0.0016. And according to my calculations, this works out to be equal to 2.6 times 10 to the minus 3 m, all right? And then the concentration calculation for COCl2, that is equal to, again, coming from the ice table, 1.00 times 10 to the minus 2 minus 0.00016. And according to my calculations, this works out to be equal to 8.4 times 10 to the minus 3 times 10 to the minus 3 m, right? So to get the moles of each of them, moles of CO is going to be equal to the moles of Cl2 because the numbers are the same for both of them. That's going to be equal to the concentration, which is 2.6 times 10 to the minus 3 times the volume. What's the volume? The same volume as before, 10.0 liters. And according to my calculation, this works out to be 2.6 times 10 to the minus 2 moles. And then we do the same thing for the moles of COCl2. And that is equal to 8.4 times 10 to the minus 3 m. This should be m here, by the way, times 10.0 liters. And that would be equal to 8.4 times 10 to the minus 2 moles. So these are the numbers here and here, and that is how we solve this problem. All right. Okay, so that's basically it for this chapter. The next chapter will be dealing with acids and bases and pH and all that good stuff. Okay, so until